All right, hello everyone. We're going to do the introduction to set theory. This is section 2.1. So in chapter 2, we're going to do a lot of set theory and kind of like theoretical statistics things. So here we go. All right, so as an overview, we can think of all the people that we know. We probably have different ways of classifying them. So something like on the picture here on the right, we have this big circle. We say like the big circle contains acquaintances. And within that circle, we also have persons that I know and like. So people that you know, people that you like. And then inside that circle, you also have like kindred spirits. And then the circle all the way in the center with the little star are your actual friends. So we have different ways of classifying just like people that we know, like really just people we know, like acquaintances, people that you like, kindred spirits, and then your friends. So we have different ways of classifying those. And so we can kind of break them down into subgroups and their subgroups and their subgroups and things like that. So really, we probably already do this a lot. We can and we do divide our world into sets. So in this case, the acquaintances would be like the entire set, and every set inside the big circle of acquaintances would be considered also a set within that original set. So we have different ways of classifying things. We just call those sets. So defining a set, we say a set is really just a collection of objects. Whatever those objects are is a collection of them. We say a set is well defined if the definition of that set is based on facts, not opinions. So whenever you work with sets, you always want them to be well-defined sets. So things like letters in the English alphabet. We know what those are. There's 26 of them. Versus like the tall people in our class. Tall is kind of subjective. I mean, if you really put like a limit on it, you say like people over the height of like 5'6" or something like that, then that could be a well-defined set. But just saying like tall people in our class, that's subjective. Someone that's really tall may not think that other people are tall. Someone that's very short might think that everybody's tall. So that is not considered a well-defined set. But saying something like everybody in our class who's over the height of 5'6", that's a well-defined set. It's a statement, it's a fact. We can determine those people. But all right, so each object in a set, we would call that the element or a member of that set. So instead of just saying like object in the set, we would say an element of the set or a member of the set. Then we use this symbol. It looks kind of like a C with like a little line in the middle, or even like an E that's kind of curvy. So this is a symbol that we use. This is how we show an object is in an element. When we actually say it, that symbol means the word in. So something is in this set. And then we just put a slash through it if we mean is not. So we would say something is not in this set. So that is the symbol that we use to show that something is an element of a set or that something is in that set that we're stating. That is the symbol. And then a slash through it if it's not. So we may also refer to the natural numbers a lot. So that could be something that you see. As a note, the natural numbers are whole numbers that are not zero and are not negative. So the natural numbers are the numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like so on, so on, so on. So like no decimals, no fractions, no negatives, no zero. So whole numbers, not zero, not negative. So an example here, we have the set of animals. So we see a bunch of animals in this picture. So there's like a fox, and that looks like a hedgehog or something. It's a giraffe. I don't know, some sort of like a squirrel or something. But either way, we see like all of this collection of animals to be a set of animals. So it's various different animals in this picture, and we would say that is a set. It is a set of animals. It is not like the set of animals. If we look at this picture, like there's no dog. So that isn't the set of animals. It is just a set of animals. So we'll get more into those details as we go on. First off, we're just going to talk through an example. What is the set of months that have exactly 31 days? So we want to think of all the months that have exactly 31 days. We can look at a calendar if you want. You can think of that like rhyme. I think it's like 30 days, have September, April, June, and November. So those are all the months with 30 days. February does not have 31 days. It has 28 days typically, although sometimes 29. So we can think of all the months that have exactly 31 days. Once we figure out what those months are actually going to be, to represent them in a set, all we would do is list them with commas, and we would put them within curly braces. So the curly ones, which we'll see here in a second. So the set of months that have exactly 31 days, that's going to be January, March, May, July, August, October, and December. All of those months have 31 days. Then here we have at the ends, we have the curly braces or the curly brackets. So they're those parentheses that are curly. That's what we indicate a set. So when we write a set, we want to use those curly braces. We just list things and we put curly braces on them. When you're listing things like this, it's important not to write like the word and. If you do, you're technically including the word and in your set. So you don't want to write and, you're just listing them with commas, finishing them off with curly braces. So that's how we would write a set. So another example we can try out, we want to state whether the following statements are true or false. So determining if something is or is not actually a set. So part A, we have S, so some set S, represents the set of states west of the Mississippi River. The question is Oregon in S? Now, the symbol for in this case looks a little funny. That's just the way that like Google writes it, so that's the way they're using it, but it's the same symbol. It's the in symbol. So is Oregon a part of this set? If we can pull up a map, we can think about it. Maybe we just know off the top of our heads. But either way, we know that west, when you're looking at a map, west means to the left. So if we look at a map, we find the Mississippi River. Oregon is going to be west of the Mississippi River. So yes, Oregon would be contained in the set S. So that's a true statement. So now on to the second one, part B. We have is cat in the set C-A-T. This is a tricky one. The word cat, C-A-T, those letters are in the set. The set is the letters C, A, and T. But when we talk about if something is a set, we need to see that exact word or phrase or letter or number in that set. It needs to actually be an element. Just because it's made up of other elements doesn't mean that it is actually in the set. So the word cat is actually not a part of this set. And that's because the set only contains the letters C-A-T. It doesn't contain the word cat. So when we talk about if things are or are not within sets, we need to see those things that we're talking about. We need to see them verbatim inside that set. The only way that the word cat would be a part of that set is if the word cat was in there, not just the letters that make up the word cat. Those are not the same things. If you want a set, the order doesn't really matter whenever you list things in a set. So that could easily say A-C-T. Well, that word is act. We're not saying that that word is in the set either. It's just letters. And the order of the letters, in this case, the order of your elements really doesn't matter. So just because the combination of some of those elements can create something else doesn't mean that that something else is actually in your set. It has to be verbatim listed in the set for it to be an element. So, all right. Moving on. We're talking about the 3 ways to actually write a set. So we can write sets using 3 different methods. The first one, which is the most common, which is what we've already seen, is the roster method. So elements in any order are listed between curly braces with commas in between the elements. So it's a list, we write commas. So elements in any order. So once again, the order doesn't matter. We can write 1, 2, 3, 4, or 4, 3, 2, 1, or 1, 3, 2, 4. It doesn't matter. Order doesn't matter when it comes to the roster method with sets. So we have examples. So we have curly braces, 2, 5, 7. So those three numbers are contained within the set. Always is something like M, so now we're labeling the set. We're saying set M is equal to the set March and May. March, comma, May. Two elements listed within curly braces with a comma in between. So the roster method is the most common that you will see. It is used a lot, although it's not the only one. So going on to the second one, we also have the descriptive method. It's pretty self-explanatory. It's a set that you just describe without actually listing any numbers or phrases or words or whatever. So these are going to be short verbal statements. So something like set B contains 2, 4, 6, and 8. You've still listed the numbers, but you're just saying that like they contain that. You can say B is the set of even natural numbers less than 10. That's another way of writing that set. So that's a better way in addition. So with the descriptive method, if we have curly braces 2, 4, 6, 8 and curly braces, then we would say set B is the set of even natural numbers less than 10. So there's a couple different things in there. We said natural numbers, those are whole numbers bigger than 0, not negative. So whole numbers that are even means divisible by 2. Those are going to be 2, 4, 6, 8, 10, 12, 14, so on, so on. And then less than 10. We see that the highest number there was 8. It didn't reach 10. We're saying it's strictly less than 10. It does not contain 10. So that would be the set of even natural numbers less than 10. So that's one way of writing it. When it comes to the descriptive method, there are multiple ways of actually saying the same thing. So it's always a little bit more flexible when it comes to the descriptive method. All right, then we have the set builder notation. Set builder notation is the most statistical way that we actually write sets. So the set builder notation lists a variable, most commonly X, sometimes Y, sometimes another letter, but most commonly X. We say it lists a variable, a symbol representing different elements of a set. So it's kind of like labeling a random like variable. You're just stating like this thing, and then you list a property. So you're saying this thing has this property. That's kind of the way that you would write that. The property of that variable goes inside a big set of curly braces, and there's going to be a vertical bar that separates the thing from its property. So over here on the left-hand side, we have some of the same examples. So at the top, we have the roster method, 1, 2, 3, 4. Commas in between, curly braces all around. So it's a set, it's a roster method, 1, 2, 3, 4. The descriptive method, one way we could talk about this set, describing it, we would say it is the natural numbers, so whole numbers, not 0, not negative, that are less than 5. 4 is less than 5, so is 1, 2, and 3. So that totally works. Set of natural numbers less than 5. Then the last one is our set builder notation. So our set builder notation also gets written in curly braces. We start off by labeling our variable, whatever that variable is. If it's up to you to decide what that variable is, X is usually the easiest one. So we say X, and then we put the vertical bar. I'm saying my item, my member, my element, X, line, property. So I'm talking about X, and here's my property. X is in N being the natural numbers, and X is less than 5. So I've written out just kind of in like mathematical language what I said in my descriptive method. So I'm saying I'm talking about X, where X is where X is in natural numbers and X is less than 5. And I put it all in curly braces. So this is the way that we write set builder notation, how we use descriptive method and the roster method. So, all right, so we're going to do an example all together. So for each set listed, we're going to write the other two forms of that set. So A, we have the roster method, 14, 21, 28, all within curly braces. B, we have the descriptive method, the set of odd natural numbers. And C, we have set builder notation, where we have Y, where Y is a natural number, and 22 is less than Y, less than 26. So we're saying Y is between 22 and 26. So, all right, so these are the sets that we're going to rewrite in all the different methods. Let's go ahead and go on over to our notes to do this together. All right, so here we have our example. For each set listed, write the other two forms of that set. Starting off with part A, we can recognize right off the bat, this is the roster method. It's things, they're just being listed, it's in curly braces, it's the roster method. So it's good to just note that from the beginning to know which one you're using. All right, so that's the roster method, meaning we need to write the descriptive method and we need to write the set builder notation method as well. So, all right, we'll use blue for the descriptive method, we'll use red for the roster method, and let's go ahead, we'll use green for the set builder notation. So starting off with the descriptive, our descriptive set, we have the numbers 14, 21, 28. If we look at these numbers, we want to realize what do these numbers have in common? 14, 21, 28, they're all divisible by 7. So that's where we can start. Say the set of natural numbers divisible by 7. So by stating natural numbers, remember we're stating like whole numbers. Although we could probably get away with not writing natural numbers in this case because we're saying divisible by 7. 7 is a natural number itself, so any multiples of 7 would also have to be natural numbers. So you could get away with this one by not saying natural numbers, but it's always good just to cover all your bases. So, all right, we're going to start this off by saying the set of natural numbers divisible by 7. So definitely a good place to start. If we just consider the set of natural numbers divisible by 7, that means we're thinking about like 7, 14, 21, 28, 35, 42, 49, and it goes on and on and on. We don't want it to go on and on and on. We only want the numbers from 14 to 28. So we have to set that. We have to state, between these values. And there's a couple different ways we could do this. I could pick a number less than 14 and a number greater than 28, and I could say between these two numbers. I can say, less than or equal to 14, or greater than or equal to 14 and less than or equal to 28. There's a couple different ways of saying it, and remember the descriptive method is a little bit more flexible. There are many different ways to actually write that out, as long as the way that you write it is correct, is really the main part here. What we're going to do, since we've seen a couple different versions already, we're going to do a new version. So we say the set of natural numbers divisible by 7, greater than or equal to 14, and less than or equal to 28. So I am including 14 and I am including 28 in this list, and anything in between divisible by 7 equals. So the set of natural numbers divisible by 7, and we can put a comma there if you want to kind of separate your thoughts out. But greater or equal to 14 and less than or equal to 28. And there's our descriptive method. So that's definitely one really good way of putting it. So, all right, so let's do set builder then as well. So set builder, now this is when we kind of identify a variable and then we give our variable specific like details. So in this case, we can pick our variable. X is usually a really good go-to, so let's just pick X. So we start off by writing the brace, we write x, and then we draw a vertical line. I'm just saying, hey, my variable is x, and now I'm going to list properties about it. So I've got x, and now I'm ready for my property. So we're saying that x is a natural number. So remember the way we write that, we would write x, and then we write the funny looking like E. It's kind of like the C with the line in it. So x is in the natural numbers. We've written that as an n. We can say and x is divisible by 7. There's probably a couple different ways to write that, but that's probably the most straightforward way. And I need to list my bounds. Remember, I'm saying it's greater than or equal to 14 and less than or equal to 28. So I'm going to sandwich my x between those two values. So I'll write 14 first. And my x is greater than or equal to 14. So I want to make sure that, the alligator is like eating the x, So 14 less than or equal to x. X is now less than or equal to 28. So same symbol, and I end it with 28. And there's my whole statement. And I could put that or end it with a curly brace. So those are the other two forms of this set. This was actually a tricky one. We started off with a tricky one that will be a little easier from now on. All right. So going on to part B, we have the set of odd natural numbers. So this is the descriptive set. It's a description. It's just a statement. We don't have any real actual numbers in there. There's no list. There's no curly braces. So this is the descriptive method. So now we want to write the roster method and the set builder method. So starting with the roster method, we know we're going to start off with some curly braces because we're listing things. And it's a set of odd natural numbers. So remember, natural numbers, whole numbers, not a zero, not negative. So just whole numbers, basically. And it's a set of odd whole numbers. If we think about odd whole numbers, the very first odd number would be considered 1. And then it's just everything that's not even. So I would write 1, 3, 5, 7, and then I'm like, this can get really long. If I notice there's no bounds, it's just a set of all odd natural numbers. As we know on, the number line goes on forever and ever. So really, when do we stop? The correct answer is probably about 4 digits. So especially with your homework and whatnot, it will want you to have 4 digits. And then once you list 4 digits, you can just write ... That would indicate that this keeps going, but I don't need to write anymore. So ... And then finish with the curly brace. So it's still within its curly braces, but I've listed 4 numbers, and I'm saying this is going to keep going by writing ... So in the roster method, the set of odd natural numbers would be 1, 3, 5, 7, ... All right. So now we can do the set builder. So now with set builder, we have, once again, we want to list a variable. You can list your variable to be anything. We could just use X again. You can use a different variable if you want. You can say T or Y. If you look for part C, it has Y instead of X. You can list anything that you want. You can say A for all that matters. You can use anything. Typically, we're always going to write X pretty much. But like I said, doesn't really matter what letter you choose. You can write whatever letter you want. We're going to go ahead and still stick with X. So we've got X, and now we're going to list X's property. So we have X. It's the natural numbers. We see those words in there, so we're still going to write X in the natural numbers in our math way of doing that, which is writing our X, writing the symbol, and then the N for natural numbers. And then we're also saying that it's odd numbers. There's definitely different ways of writing this, but the most straightforward way is just by saying, and X is odd. So we'll say, and X is odd. The set builder notation is kind of like the roster method and the descriptive method combined, just a little. So, all right, now we can go on to our last one. C, we have y, where y is a natural number and y is between 22 and 26. 22 is less than y, which is less than 26. So we see curly braces, we got that vertical bar in there, we're talking about y, there's a property, so this is the set builder method. All right, so starting off with the roster method. All right, so we're talking about y, whatever y is. Y is a natural number. Great. Whole number, positive, not zero. And it's greater than 22, less than 26. Now, if we notice, there's no little line underneath those symbols. So we're talking strictly greater than 22, strictly less than 26. The next number greater than 22 is 23, and the number that's less than 26 is 25. So really, I don't include 22 and 26. I only include numbers greater than 22 and less than 26. So when we write out a roster method, the first number greater than 22 is 23. And then it's just natural numbers, so I keep going, 23, 24, and 25. If I notice that's the last number I can list, I cannot list 26. It is not included. We're saying that y is strictly less than 26. So that's where I finish. That's where I end. That's the end of my natural numbers. So I only have 3 digits. Now we can go over to our descriptive method. Now the descriptive method, we do have that it is a natural number and it does have like a range there. So let's write that out. We say that we have the set of natural numbers. And before, when we were up here at the top, we had the greater than or equal to and the less than or equal to. In this case, we can write greater than 22, less than 26. But another way of writing this is saying the set of natural numbers between 22 and 26. So between 22 and 26 indicates not included. So not including 22, not including 26, but every number in between. So that's another way of writing it. Although you could still definitely write greater than 22 and less than 26. That's another way of writing it. So, all right, so just seeing a couple different ways to write out our different sets and the ways that we can actually kind of depict those. So, all right, let's go on back over to our lecture. All right, so we finished up that example. So moving on, we can define an empty set. So what if there's nothing in a set? What if there isn't anything there? We'd say a set with no elements is called the empty set, also sometimes called the null set. And we use either a set of curly braces with nothing in between, or what looks like an O with a slash through it. Either one of those represents the empty set. So curly braces with nothing inside, or the O with a slash. That's how we write the empty set. That's how we say there's nothing here. If there is anything, literally anything, written between curly braces, that is a set. That's not an empty set. If you put a period in between curly braces, that is a set. It is the set of period. That's all it is, but it still means something. So if there's anything inside curly braces, it automatically means it is a set and it's not empty. So this means that writing curly braces with the empty set symbol, the O with the slash, that's not an empty set anymore. You put something in between curly braces. Didn't matter what that something was, you've now made it a set, not an empty set. So that would not be correct. If you wrote that, that does not mean the empty set. You have to write the O with the slash by itself or curly braces with nothing in between. Same goes for like double curly braces. Having double curly braces still means that that's technically a set. So just remember, anything within curly braces automatically is a set, not the empty set. And the O with the slash through it is the empty set, unless you've put it in curly braces, then it's no longer an empty set. So just be aware of those notational things to worry about. But that's how we do an empty set. An example of an empty set would be something like the set of living woolly mammoths. There are no living woolly mammoths. They are extinct. So that would be an empty set. There's nothing in that set. Just because the number is actually 0, if we put 0 inside the set, that would not be an empty set. So we have the empty set. It does not exist. So that's why we write the empty set instead. So things like that. Something else could be something like everyone in this class is like, I don't know, somewhere weird. Or you could say, you know, every person in this class has some specific ridiculous like attribute. And if the number is technically 0, we would just say that's the empty set. It doesn't exist. So there is a difference by saying like putting a number in the set, by saying like putting a 0 in curly braces is not the empty set. If there is nothing of that, or it doesn't exist, or there isn't anything, you would say that's the empty set. You would not say that's the set of 0, because that's the set of one thing, and there isn't anything in what you're talking about. So there's a little bit of a difference. Now we can also do something called finding the cardinality of a set. So the number of elements in a set is called the cardinal number. So the cardinal number is the number of numbers in your set, or the number of elements in your set, or the number of members. So something like the set R is equal to 2, 4, 6, 8, 10. So it's the set of 2, 4, 6, 8, 10. That has a cardinal number of 5 because it has 5 elements. 2, 4, 6, 8, 10. That's 5. So it's 5 elements. So we say that that is the cardinality of your set. So the cardinality of set R is 5. We can depict this mathematically as saying n, and then big parentheses, whatever the set name is, parentheses equals 5, or n of R equals 5. So that's how another way that we write that kind of mathematically. We see here there's this big 5 over here. It has the numbers 2, 3, 6, 9, 13. So if those are all the elements of a set, the cardinality is 5. There's 5 numbers in that set. So let's go ahead and try some out. So we want to find the cardinality of the following sets. A, we have the set T. T is kittens, puppies, rabbits, hamsters, mice, guinea pigs. So if we think about this, we have kittens, puppies, rabbits, hamsters, mice, guinea pigs. That is 6. So 6 elements in set T. N of T equals 6. So that's a cardinality. Then for part B, we have our set S. Now it's in set builder notation, so it's a little tougher. We have X, where X is greater than 0 and less than 10. Remember, these are strict inequalities. This means strictly greater than 0, strictly less than 10. In this case, it's not listed, but we're going to assume this is talking about natural numbers. If we're talking about every number ever, it's technically going to be like infinity. So we're going to assume this is natural numbers, the numbers between 0 and 10. So I don't include 0. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't include 10, saying it's less than 10. That means that there are 9 members, 9 elements. So n of s is equal to 9. So you're just going to count up the actual elements. But let's say you don't really have a list. For part C, we have the set W, where you have X. X is a letter of the English alphabet. So now you have to know how many letters are in the English alphabet. You could sit there and go A, B, C, D, E, F, G, something like that. If you want, you could look it up. Either way, but you should realize that there are 26 letters in the English alphabet. So that means that there are 26 members of that set. So N of W equals 26. So that's how we find the cardinality of the following sets. You can count purely on your fingers. You can have an idea. So like the letter of the English alphabet, you can have like a range of values, like how we saw from 0 to 10, or you can just purely have a list like we had in part A. So, all right. Now we can classify sets as finite or infinite. So a set is finite if it has no elements or if it has a cardinality that's a natural number. So the empty set is a finite set in this case, or as long as it has a cardinality that you can actually write. So something like the set mouse, rat, squirrel, X, Y, Z. Both of those have cardinality of 3. You can count them. You also have like something like 1, 4, 9, 16, 25. That's cardinality of 5. You can count those. But a set is infinite if its elements are never ending, aka not finite. So something like 10, 20, 30, and then you see those dots. If you see the dot, that definitely means it's infinite right off the bat. That's not finite. It's only finite in the small case that it actually ends with a number, but I don't think that that will be something that you see very often. But it's potential. You could see it. So infinite, because it just has dot, it means it's going to go on forever. If in case it said 10, 20, 30, and then went dot, comma, 100. If it said something like that, that does mean that it's going to end at 100. It's just that whoever was writing it got really tired of writing numbers and decided to write dot, instead. But basically, if it ends with dot, it will be infinite. Then we have something like the set of songs that can be written. If time has proven anything, there are so many songs that apparently can be written and produced and all that kind of stuff. So there's always going to be songs that can be written and whatnot. So that is technically going to be infinite as well. So that will just go on forever and ever. Or n, the natural numbers. The natural numbers are infinite. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, dot. So those are infinite sets as well. So now how to decide if two sets are equal or equivalent. So we have two different ideas when we talk about these like situations. So if we say something A equals B, if we're talking about two sets, A and B, they are equal. That means they have the exact same elements. The order does not matter, but they have to have the exact same elements. So if P equals 3, 5, 8, and 10, and Q equals 8, 5, 3, and 10, P equals Q. The order didn't matter, but they do contain the exact same elements. They both contain 3, they both contain 5, they both contain 8, and they both contain 10. So P equals Q. Then we have equivalent. So equal was definitely kind of like what we expected. Now we also have equivalent. The equivalency sign is symbolized by having the equal sign and a squiggly line above it. So that means equivalent. We have two finite sets, so they do have to be finite for this. C and D are equivalent if they have the same number of elements, meaning they have the same cardinality. The elements themselves do not have to be the same, but they have to have the same number of elements. So we could say something like the set S is 1, 2, 3, 4, 5. The set T is 6, 7, 8, 9, 10. S and T are equivalent. They both have, in this case, 5 elements. But the elements are not the same. They are the same size. So that's the difference between equivalent and equal. And if you think about it, anything that's equal is going to be the same size. So anything that's equal is always going to be also equivalent. You can't be equal without being equivalent. So you can have equal and equivalent. Then you can have just equivalent, meaning they don't have the same members or they don't have the same elements, but they are the same size. And then it can also just be not equal and not equivalent as well. So all equal sets are equivalent, not all equivalent sets are equal. Two sets are called 1 to 1, if each unique element can be paired with another unique element in each set. So 1 to 1, if you can pair them like uniquely within the sets. So that would be something more along the lines of something that is equivalent. So instead of having the set of like 3, 3, 3, 3, 3, you would have a set of like 1, 2, 3, 4, 5. And then your other set is 1, 2, 3, 4, 5, or 6, 7, 8, 9, 10, or something like that. Basically, you're just not listing the same number multiple times. That's what 1 to 1 is typically going to mean. So, all right, that's what the difference is between equal and equivalencies when it comes to sets. So, all right, we're going to try a couple out. So we have an example: determine if the following sets are equal, equivalent, neither, or a combination of either any of these things. Basically, equal and equivalent. So, all right, first we have A. We have the set of D, O, G, and the set of C, A, T. Cat and dog. But remember, the words aren't actually in the set. So we have DOG and CAT. They obviously don't have the same elements. DOG and CAT are not the same letters, but there's 3 in DOG and there's 3 in CAT. So they have the same cardinality, which means they are the same size, which means they are equivalent. So those are equivalent. They have the same number of members. Now going on to B. We have TOP and POT, top and pot. So we see, yes, they do have the same letters. They both contain T, they both contain O, and they both contain P. And there's no extras either. So yes, they do have the same elements. They both have cardinality of 3. So they are equivalent and they are equal. So equal and equivalent. Same exact members, which also indicates the same cardinality. Then we have C, this last one. We have the set of run and the set of R, U, N. So this is an example of having a word versus the letters that make up that word. The word is run. That's the only element in that set. In the other set, the set of R, U, and N, there are 3 members in that set. There are 3 letters. They do not have the same cardinality. The set of run is just one cardinality, and RUN has a cardinality of 3. They do have the same elements, kind of. They have the same letters, but remember the elements of the second set are R, U, and N, and the element of the first set is just the word run. So they do not have the same elements, they do not have the same cardinality, therefore they are neither. So they're not equal and they're not equivalent. It was not an example in this one, but it's important to note that just because something has the same elements, if another set has more elements, they're still not equal just because it has some of the elements that was in like one set, not the other. So something like the set of XYZ and the set of WXYZ. They're not equivalent because they don't have the same number of elements, and they're not equal because they don't have the exact same elements. You have to have the exact same elements for them to be equal. So those would be neither as well. So all right, that wraps up section 2.1. So identifying what a set is will help us with the rest of chapter 2 when we establish more things about sets. So here we go. In summary, in section 2.1, we learned how to define a set, how to write sets 3 different ways, how to define an empty set, how to find the cardinality of a set, classifying sets as infinite or finite, and deciding if 2 sets are equal or equivalent. So, all right, that wraps up section 2.1, and I'll see you in the next one.